All right, we're ready for section 3 in the prerequisite chapter of calculus. This one's on functions and graphs. Now, I will tell you that this particular section is practically a chapter from a traditional algebra book, so there's quite a bit, and most of it is review, so I'm going to run through it quickly, but I am going to try to do a few examples to help you out with this, just to make sure that you feel comfortable before we get into chapter 1 on limits. Section 3 here has to do with functions and their graphs, and of course with functions you have to have a definition, and before we can start with the definition of a function, we define what we call a relation. A relation between two sets x and y. Notice my notation here, kind of a capital looking Roman numeral x and a capital looking Roman numeral y, although there's no Roman numeral y. These represent two sets of numbers. It's a set of ordered pairs, each in the form xy, where x is a member of the set x and y is a member of the set y. Now, any set of ordered pairs, any kind of ordered pairs, would be considered a relation. But a function is a special type of relation. It is a relation between x and y that has the property that any two ordered pairs that have the same x have to have the same y. You cannot have the same x with two or more different y values. Now, we usually refer to in functions as x is the independent variable and y is the dependent variable. And you guys should be familiar with that, which leads us to the formal definition of a real valued function. A real valued function of a real variable, let x and y be sets of numbers, a real valued function f, and we like to use lowercase letters like f or g or h, of a real variable x from set x to set y is a correspondence, okay, that assigns to each number x that's in the set of x here exactly one number y, which is in the set of y. So again, you can't have the same x with more than one y, and we typically refer to as the set x as the domain of the function. This is the set of values that we substitute in for the variable x, the independent variable in the function. Now, the y value that we get after we plug in this x, okay, is the image of x under the function f and is denoted by f of x. Now, the range of a function is a subset of the set y. Now, typically we think of set y as the range, but it could be a larger set of values, perhaps the set of all real numbers, and the range of the function happens to be just the positive numbers. So it is a subset of the set y and consists of all images of the numbers in x. Now, you may remember the vertical line test being a way to determine whether or not, given a graph, if we have that of a function, because we have to have this property that says for each number x there's exactly one number y. Okay, now most of the time we define functions what we call explicitly, where we have y in terms of x, y all by itself on one side, and on the other side some expression in terms of x. Here's an example. This is the equation of a line from last section, y equals 3x minus 7. But a lot of times when we're talking about functions, we replace the y with the f of x. That's the idea that we have it defined explicitly, because we want f of x to be all by itself on one side, just like we want y to be all by itself on one side. Now, if we had rewritten this and put the x's and the y's on the same side, then we'd say that the function is written implicitly. But when we have y all by itself on one side, then we can use the function notation, the f of x. Now remember, f of x is not the function. F is the function. F of x is a value, a y value of the function. It's the same as the y. Okay, it's the same as the y here. Function notation is nice in that you pretty much can tell exactly what's going on, especially when you start plugging in values for your variable. Function notation is best for functions that can be written explicitly. That's what I was saying before. You want the f of x all by itself. That's your dependent variable. X is still your independent variable. And it's also used for evaluating. Notice here, I have f of x equals x squared plus 15x. This is a function. And it asks you to find f of 2, which is a fancy way of saying what is y when x is 2. So if I had this written as y equal x squared plus 15x. I don't, but if I did have it written that way, and I asked you to plug in 2, we might write something like y when x is equal to 2 is equal to 2 squared plus 15 times 2, which we can figure out, and I believe that's 34. Well, we don't need this weird looking notation here. There's nothing wrong with it. We just don't need it if we can use function notation. And right, f of 2 means you're substituting 2 in for the independent variable, 2 squared plus 15 times 2, and that turns out to be 34. All right. Now, these guys here, f of x equals x squared plus 15x, and g of t equals t squared plus 15t, they look very similar. Well, they do describe the same and define the same function. It's just that you have a different name for the function. This one is f, and this one here is g, and you have a different independent variable, but everything else is exactly the same. We're just mostly used to having our independent variable being x, but later on, when we start doing some applications involving time, you'll see that t comes in handy because typically we'll represent time when we're working those kinds of problems. All right, now, here's some more evaluation. It says consider f of x is equal to 3x squared plus 5x, and they want you to evaluate. Now notice here, the first one is pretty straightforward because it's just a number. For a here, f of negative 2 means you're going to substitute negative 2 into the rule there, 3x squared plus 5x. So I'm going to plug negative 2 in both spots. And then I just use my order of operations. This is going to be 3 times 4. This is going to be negative 10. And it looks like I'm going to get an answer of 2. Well, now it gets a little trickier because it's not a number that you're plugging in, but it's an expression, a plus 2. But we're going to work it the same way. We're going to substitute a plus 2 into our independent variable x. So I'm going to write f of a plus 2 is equal to 3 times the quantity a plus 2 quantity squared plus 5 times the quantity a plus 2. Well, 3 times the quantity a plus 2 quantity squared, I'm going to simplify this a little bit. I'm going to have to square this out, so that's a squared plus 4a plus 4. Over here I can distribute, get rid of the parentheses, that would be 5a plus 10. Speaking of distributing, I have to distribute up here. I have 3a to the second plus 12a plus 12 plus 5a plus 10. And combining like terms, I'm going to get 17a plus 22, 3a squared plus 17a plus 22. Now, if I asked you to work a problem like this and you stopped right here, I probably wouldn't get you full credit here because you can't simplify the expression, and typically we want to unless the directions to the problem tell us otherwise. Now, this really looking weird expression over here, we're going to use him quite a bit, especially in chapter 2 when we get there. It's an expression that has its own name. It's sometimes called the difference quotient expression. Notice the difference here in that you're dividing this difference by delta x, which is a quotient. Now typically you say, well, what the heck is the little triangle? The little triangle is the Greek letter delta, and I think it's capital actually, the capital delta. And when you in mathematics, delta typically means the change in. So this would be the change in x. So maybe as one x value changes to a different x value, this would be the difference between the two, the change in x. So I'm going to write, very similar to what I just did here, I'm going to write this one here using this guy here as my rule. And here we go. I'm going to write f of x plus delta x minus f of x all over delta x to be f of, well, the very first part I'm plugging x plus delta x in for my variable x. Now that seems also kind of weird because you're plugging in something bigger than what you're plugging it into. That's okay. All of this is going to go right in there and right in there. So I get, let's see here. Well, I almost jumped again here. Let's get rid of that f. So I am plugging in x plus delta x in here. I'm going to get 3 times x plus delta x squared plus 5 times x plus delta x. A little simplifying coming up there. That's this part right here. That's this part right here. Now I'm going to subtract from that f of x. And that's f of x, the original. So in parentheses, 3x squared plus 5x. And then I'm going to divide all of this by delta x. Now, most of the work here is not the part that I've just done. Most of the work is simplifying this. So I'm going to square this out. I get 3 times, this would be x squared plus 2 times x times delta x plus delta x squared. I like to put delta x in parentheses like that when it's being multiplied times something or being squared raised to a power. And then all of that minus, now here I can distribute. I get minus 5x plus, I almost wrote plus. In fact, I did write plus minus because no, I take that back. It is not minus 5x squared because I cannot read my own thing there. No wonder I was right the first time. Plus 5x plus 5 times delta x minus, now this is like a negative 1 there. Glad I caught that early. Minus 3x squared minus 5x. I guess I was thinking of that subtraction sign. At least that's what I'll say in court. Let's go ahead and put this all over delta x here. All right, I have to distribute. So I have 3x squared plus 6x times delta x plus 3 times delta x quantity squared plus 5x plus 5 times delta x minus 3x squared minus 5x all over delta x. Now, fortunately for us, this is going to simplify a little bit, which is good because I'm about out of space on my paper here. I can cancel this out with this, and I can cancel this out with this. And notice here, I have 3 terms remaining in my numerator, and all of them have at least one factor of delta x. So I am going to factor out that delta x out of those 3 terms, and I'm going to get 6x plus 3 times delta x plus 5. And all that's being divided by delta x. You can probably see why I went ahead and factored that factor of delta x out, because they're going to simplify, and this is going to give me 6x plus 3 times delta x plus 5. Now that may not look like much right now, but when we get to chapter 2, that's going to look like the thing to do. So we're going to try to get used to this expression, which again is called the difference quotient expression. All right. Now, when you have a function, you have a domain and you have a range. Now, if the domain is given or is described explicitly, like in this first example, I have the function f of x is equal to the square root of x for all values of x equal to 1, 2, and 3. So I have a limited domain here. Then we say that the domain is defined explicitly. But if they do not give us something like this, they just give us this guy right here, f of x is equal to the square root of x. Then we assume that the domain of the function is every real number that makes sense, that does not give you, for example, an imaginary, does not give you division by 0. So in this case, since we cannot take the square root of a negative number, because the square root of a negative number would be an imaginary number, we say that the domain of f, using interval notation here, is the set of values from 0, including 0, to infinity. So this won't always be given. They may ask you for this. This may be something that you have to write down. But if they just give you the function without a specific domain, then we say that the domain is described implicitly, and we put down the largest possible domain that we can. Now in the next example, it says we have a multi-ruled function. We're to find its domain, and we're to sketch the graph. Now, it doesn't really matter which order you do this. You can do the sketching first and then find the domain, or you can find the domain and then sketch it, because finding the domain is typically a pretty easy thing to do. You just have to look at the rules of the function, because it's multi-ruled there too. Or this is sometimes called piecewise defined, because it has 2 pieces here. But in this case, all the values are given right here. You can see here that if x is less than 0, you're using the rule for x squared, and if x is greater than or equal to 0, you're using the rule of the square root of x. So the domain here of f, big capital D with a lowercase, like a subscript, lowercase letter f, is equal to all real numbers, because every real number is in one of those 2 rules. Now, as far as the graph, we graph it in pieces, thus the name piecewise defined. For values of x less than 0, we have x squared, which is probably by now you're pretty familiar with the idea that this is a parabola whose vertex is at 0, 0 that opens upward. Well, in this case, we're not going to include 0, 0. So I put a hole there in the graph, but then I know if I plug in -1, I get +1. If I plug in -2, I get +4. And I'm going to try to sketch this halfway decent. And there's your first part of your graph here. Now we're not done, because that's only one of the rules. In the other rule, we have y, or f of x, is equal to the square root of x for all values of x greater than or equal to 0. Well, if you plug 0 in, you do get 0. That fills in the hole. If you plug in 1, you get 1. If you plug in 4, you get 2. You probably should be familiar with the graph of y equals the square root of x being kind of like a half of a sideways parabola, for lack of a better description. And so now I'm going to go ahead and graph that out. Okay, remember when you're doing graphs, always label your axes. Okay, now there are different kinds of functions, some functions more important than others. One of the more important functions is what we call a one-to-one function, because those types of functions, and we're not going to talk about it too much right now, but those types of functions you may remember from your pre-calculus days have inverse functions. A function from set x to set y is one-to-one if for every y value in the range there corresponds exactly one x value in the domain. Because it's a function, every one of the x's has exactly one y, but because it's one-to-one, every y has exactly one x. Now, if you were to graph y equal x squared, which is a parabola, which would be this part and then this part also, it would have one y value that would correspond to two x's. It's not one-to-one. Okay? A one-to-one function, you may remember, passes the horizontal line test, kind of like the vertical line test, but this tests whether or not it's a one-to-one function, horizontal line test. And that is if you can draw no horizontal line that crosses it more than once, then it is a one-to-one function. Another thing has to do with the idea of a function from x to y is considered onto, and I know that sounds kind of strange. It's not something that they use in a lot of the newer textbooks in high school. It's more a little bit old school. If the range consists of all values in the y. Now you may remember I said earlier on when I was defining a function that the set y could be actually bigger than the range, but if the range is exactly the set y, then we say that the function maps x onto y. All right, now there's a lot that goes into this next little part. In fact, this whole chapter is just chock full of information, but we're talking a little bit about the way you can transform graphs given a what we call sometimes a parent function. Given one graph, we can create a family of graphs by transforming the graphs using either shifts or translations is probably a better way to write that. Translations. Vertical and horizontal translation, shifting it right, left, upward, downward. Vertical and horizontal dilations, that's where you stretch or you shrink them. And of course, reflections in the x-axis or in the y-axis. We can get all sorts of different kinds of looking graphs, but they're all going to have the same basic shape. Now, where I grew up, there was a family that lived in town. One of the girls in the family was my age. In fact, a buddy of mine dated and married her, and their last name was Green. Nice family. I had the uncle as a teacher one time in summer school, but you could tell they were from the same family because they had the same eyes. They looked exactly the same in the eyes. You could tell that they were brother and sister or sister or brothers. It was a big family. I think there were like 7 or 8 kids. Just by the looks of their eyes. Even the uncle had the same look. So what you have when you have a family of graphs is they have the same look in some manner, but they may have been shifted, translated, they may have been stretched or shrunk, dilated, or they may be reflected over one of the two axes. Here are your parent graphs that you should have some idea about. I'm going to try to leave off the bottom ones a little bit because we haven't really talked about trig yet. But here are some of the algebraic ones. You have your constant, your linear, your absolute value. You have the greatest integer function, which we talked about in pre-calculus, but we're going to talk a little bit more about this in this class as well. It's a great problem when we get to the topic of continuity. Then you have your parabola that we just graphed before, the quadratic function. There's a basic cubic. There's your square root guy that I was just looking at. Here's your cube root guy. And then you've got even kind of jumping the gun here a little bit with exponential and logarithmic functions, which we're going to talk a little bit more second semester. But we also have the reciprocal, or the sometimes we refer to this as a hyperbola. The basic one, y equals 1 over x. And then here's an example of a rational. And you can see different dotted lines there that are asymptotes, which again we're going to talk a little bit about. All right, so these are some of the ones that you, not all of them, but these are some of the ones that you should have some familiarity with. Okay. Now, the elementary functions that we're going to deal with probably 80% of the time are the ones that you guys studied last year in pre-calculus. They're your algebraic functions, which are polynomial functions, radical functions, rational functions, your trigonometric functions, and then of course your exponential and logarithmic functions. And as I mentioned, we've studied those in pre-calc, but we'll get to both of those again later on in second semester. So we'll start off with probably the most basic, which would be the polynomial function. A lot of information here, guys, which are functions that can be written in the form f of x equals a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus, and so on, all the way to a sub 2x squared plus a sub 1x to the first, or just x, plus a sub 0. This guy here is referred to as the degree of the polynomial. It's the largest exponent of your independent variable. And all these a's here that we have written out here, those are your coefficients. Although, typically we refer to this guy not so much as a coefficient, but as the constant term. Now, theoretically, a sub 0x to the 0, because x to the 0 is 1, and you can kind of think it in terms of a coefficient, but in a lot of books they just refer to it as a constant term. Now, the degree here, x to the n, the coefficient of this highest degree term is referred to as the lead coefficient or the leading coefficient. And as I mentioned, a sub 0 would be the constant term. Okay. If you have a polynomial of degree 0, then you have a constant function. Degree 1, it's a linear function, like a line is one-dimensional. Degree 2 is quadratic function, and some students wonder why they use quad, because that's 4. But in the old days, squares used to be called quadrangles because of the 4 right angles, and so they kind of get it from that expression of the quadrangle. It's a two-dimensional shape, like a square is two-dimensional shape, and it's degree 2. A cubic, you guys know from your geometry days that when you found volume, you had cubic units, degree 3 cubic units, and then there's quartic, quintic, and so on up the line. And if you go up to like an arbitrary degree n, we refer to it as a polynomial function of degree n, or the nth degree of the polynomial function. The rational functions are the ones that can be kind of like written as fractions, just like rational numbers or fractions. Rational functions have the form f of x equals p of x over q of x, where q of x doesn't equal 0, so you can't divide by 0, and both the numerator and the denominator are polynomials. All right, now, here's a nice little definition. An algebraic function, which we talked about, I mentioned here as one of the elementary type. An algebraic function is a function that can be expressed as a finite number of sums, differences, multiples, and quotients, and radicals that involve x. Now, if it's not algebraic, then we refer to it as a transcendental function. Functions that are not algebraic are transcendental. Transcendental would be like your trig functions. Okay? Now, functions have their own algebra. It's kind of weird to think of that, but functions have their own algebra. You can add them, you can subtract them, you can multiply them, you can divide them. There's an identity function, there are inverse functions, there's even closure, which means that if you add two algebraic functions, especially like, for example, polynomial functions, you get a polynomial function, you get another algebraic function. But there's a fifth operation, and that fifth operation used to combine two functions is the operation of composition, when we compose functions. So that is a little lip there that gets stuck in. I'm going to define what we mean by when we compose functions. Composite functions. Let f and g be functions. The function given by f, and this is a little circle there, this is not fog, f circle g, it's not an O, okay, it's not a 0, it's just a little symbol there that looks like an O that we read as a circle, f circle g of x, or f compose g of x, although that's not used very often, is f of g of x. Notice you have an inside function and an outside function, and this is called the composite of f with g. The domain of f circle g is the set of all x that's in the domain of the inside function, so that when you take and plug these numbers in for x and you take g of x, you get all these images, that ends up being part of the domain of the outside function. So notice here, I'm going to map x to g of x, all right, And this g of x has to be in the domain of f, has to be part of the domain of f, so that we can now map g of x using this is using the function g, this is using the function f here, so that we can get to f of g of x. Or we can kind of skip the middleman and we do the composition of the two. Now, you've had this before, but it's always a stumbling block at times. And so what I'm going to do is show you a couple of simple examples here. I have here in this case, f of x is equal to 4x minus 3, and g of x is equal to x squared. I want to find f circle g, and I want to find g circle f. By the way, composition is not necessarily commutative, so you have to be careful there. It's not going to always be the same. In fact, usually it's not. So we'll start with f circle g of x, which is, all right, f of g of x, which is, let's see here, one more parenthesis, f of g of x, which is x squared. G of x is x squared. So now I'm going to plug x squared into the rule for my function f, in for the variable, independent variable. So now, in for x, I plug in x squared minus 3. And then I would simplify this if it simplifies, and this one doesn't. That's just what we get. Now let's try it the other way around and see if we get the same thing. G circle f of x, I don't think we're going to, is g, I'm sorry, I kind of spoiled that, didn't I? You were probably just, just full of suspense to decide whether or not that these turned out to be the same. G of f of x is g of, now in for f of x, I replace it with 4x minus 3. And now I'm going to replace all of this into the rule of g for my independent variable x. So I end up with 4x minus 3, and that gets squared. Now I'll probably go ahead and multiply this out. I get 16x squared minus 24x, I'm doing a little FOIL there, equals 9. And there, as you can see, I get two very different looking answers. Okay, let's try it down here. Now I went ahead and threw in a trig function, even though we haven't really talked too much about trig yet. We'll do a little bit of that in section 4, kind of get you a review of some things in trigonometry and from your pre-calculus days. F of x is equal to 3x plus 1, g of x is equal to the sine of x. Let's find f circle g and g circle f. If you hadn't already had this in pre-calculus, I wouldn't have bothered throwing it in at this particular point without defining it, but I think we can deal with it. This is f of g of x, which is f of, now g of x is the sine of x, and now I'm going to plug the sine of x in for my independent variable there in the rule for f, 3 times the sine of x plus 1. All right, let's see what happens if we do it the other way around. I can almost guarantee you we're not going to get the same thing. This is g of f of x, which is g of 3x plus 1. So now we're going to substitute 3x plus 1 in for the independent variable here. So that gives me the sine of, in parentheses, 3x plus 1, because I'm taking the sine of the entire expression. Don't forget the parentheses there. And it's not like you can distribute this as far as this goes. This simplifies, and that's simplified, and you can see they're not the same. So as I mentioned, when you compose functions, it's not necessarily a commutative operation. All right, now we're finishing this stuff up. This is a very long section, and I know this you're getting probably more than just a little bored listening to my voice going through all this, but let's consider the function f of x equals 2x minus 4. This is a linear function, degree 1. We know that when you have a linear function, you have the graph is a line, and unless it's a vertical line, which this one is not, because I can write it in slope-intercept form, it's going to have an x-intercept and a y-intercept. I guess it could be horizontal and wouldn't have an x-intercept. But in this case, the x-intercept is the ordered pair 2, 0, because we know when we find the x-intercept, we plug 0 in for y and we solve for x. Well, what's related with this is that the x value of the x-intercept is also referred to as the 0 of the function, because if I take f of 2, notice that I am going to get 0. It's not what happens when you plug 0 in. It's like, what would you plug in to get 0? So the 0 or zeros of a function are the solutions to when you set the function equal to 0 and you solve for x. They like talking about zeros. You may remember we talked about zeros when we were talking about polynomial functions and oh my goodness, I'm glitching. When we did the rational zero function and such back in our pre-calculus days. All right, let's go what we have here. And we are on the last page of notes for this section, thankfully. All right, now, we talked a little bit about symmetry in the last section. Not a great deal, but we did talk about symmetry with respect to the x-axis, to the y-axis, and to the origin. And in function terminology, a function is considered to be what we call an even function if its graph is symmetric to the y-axis, and it's an odd function if the graph is symmetric to the origin. Now, there is no function that is symmetric to the x-axis because it would fail the vertical line test. So when we're talking about function terminology and we talk about an even or an odd function, even means symmetric to the graph is symmetric to the y-axis, and odd means that it's symmetric to the origin. And there are tests very similar to the symmetry test to determine if you have a function that's even or odd. The function y equals f of x is even if you replace x with the opposite of x and you get back to the original. F of the opposite of x is equal to f of x, and it's an odd function. The function y equals f of x is odd if f of the opposite of x is equal to the opposite of f of x. So I have three examples. We're going to determine whether they're odd, even, or neither. I'm going to start off with A here. To see if this is odd or even, I am going to replace x with the opposite of x. That gives me the opposite of x cubed plus the opposite of x, which the opposite of x cubed is like the opposite of x times the opposite of x times the opposite of x. Negative times negative times negative is negative x to the third, and plus the opposite of x, of course, is the same as minus x. Well, this is, if I factor out a negative 1, x to the third plus x inside, and of course that was the original function. So this is equal to negative 1 times f of x, or the opposite of f of x. So I have shown that this is an odd function. Now again, when you're answering problems like this and you show all this work, but then you make me assume that I know if this is odd or even because you don't write it down, you have a tendency to lose points. So be sure to answer the kind of question. In this case, it's an odd function. Now again, this is kind of jumping the gun a little bit because there's another trig function thrown in here. And you may or may not remember, but we're certainly going to review it some in the next section, but I'm going to tell you right now that g of the opposite of x for cosine of x would be the cosine of the opposite of x. And the cosine of opposite of x is defined back in your trig days as the cosine of x, which means that I have back to the original function, g of x. So this is an even function. You may or may not remember, but I'm going to tell you that cosine and secant are even functions. Sine, cosecant, tangent, and cotangent are all odd functions. One to go here. Well, we've had an odd, we've had an even. I bet this one's an either. Let's find out. H of the opposite of x is the opposite of x to the second power plus the opposite of x plus 1. Well, the opposite of x times the opposite of x is x squared, because negative times negative is positive, but I have a minus x in the middle. And there's no factoring, there's no anything that I can do to make this get back to this original or make it get to the opposite of this. It's neither one. So in this case, I write down, oops, got to spell it right. I write down neither. And that finishes up a very long review section there. Sorry, I got kind of tilted there. A very long review section here for section 3 of the prerequisite chapter.